There are many different things in the Internet of Things, or even the industrial Internet of Things. These things are combinations of mechanical, electrical, and information systems. Each has a different purpose and intended end use. Therefore, there are many domains of applications expertise that must be carefully considered before deploying an IIoT solution. For example, just in manufacturing alone, there are material removal processes, material addition or joining processes, assembly processes, and so on. In order to correctly deploy an IIoT system for any given domain, the physical phenomena associated must be carefully observed and understood. This then drives the selection of sensors, which in turn drives the selection of signal processing, computing hardware, other software, algorithm development, ultimately culminating in actionable information regarding the current state of the system.
I think the first question on domain expertise, Professor Lang.
Absolutely. So, Professor Lang, in terms of research and development insights and sort of the impact on IIoT, we sort of discussed a little bit of that earlier, but maybe if you can give some interesting examples of how, maybe foundational, transformational technology development in the R&D world has had impact, and maybe specifically in this area of energy, load monitoring, things of that nature that you had mentioned before.
Sure. I can give three examples, one of which I'll skip quickly. I spoke about state estimation for power systems. That's something that came out of our lab, literally Fred Schweppe, about 40 years ago, and it has had a huge impact on the operation of the grid. So I'll pick rather two newer ones. Maybe the first is sort of a systems example, not mine. One of my colleagues in the lab from Steve Lieb. He's developed something called a non-intrusive load monitor. And the story goes something like this. In a home, to take as an example, light bulbs, appliances, dishwashers, refrigerators, washing machines, etc., heaters, computers, and so forth, they all have different turn-on transient signatures. They all have different turn-off transient signatures. They all have different real and reactive power signatures when they're operating. So it is possible, and this has been demonstrated in the lab and in various homes, it is possible on the direct measurements of the mains entering into the home to determine precisely what is on inside, how many light bulbs there are, how much power they're using, is the washing machine running, is the dishwasher running, is the water heater running, is somebody taking a shower, on and on. Are the computers running? You can literally tell how many people are in that house and what they're doing, and if you had a floor plan, you could tell what room they're in. It's a bit scary. But when I said that you can extract complex information from simple measurements, I think this is a really, really good example. And now imagine extending that into a factory for a real IIoT application. By looking at power, you could tell which machines are running. Are they healthy? Are they not healthy? Are they functioning? Are they doing their job? Are they skipping their job? And so forth. All from very simple power measurements with a sophisticated software application behind it. So that's one example that I would like to leave you with. A second example that's much more focused, I'll take from my own work, is focused on motor-operated valves. A motor-operated valve is a large piece of equipment that has a motor, drives through a gearbox, a long shaft, which opens and closes a valve that will pass or block fluid flow. So it might be in a processing plant, for example. Again, looking at the power signature, if you measure voltage and current on one of these motor-operated valves, you're essentially measuring power, but there are signatures on there which allow you to determine on the other side of the motor what is its speed and what is its torque. Now that speed and torque, which is being provided by the motor, is actually also being received by the motor-operated valve. They're both operating in the same way in that manner. And so on that torque signature and on that speed signature is a tremendous amount of information, which you can get from the electrical side. So for example, in a large motor-operated valve, we were able to see the gear tooth meshing, and with a broken tooth, you can identify that. We were able to look at the packing, which is around the shaft. We could tell when the packing was loose, when the packing was tight. We could look at valve seating. At that instant when the valve closes in the seat, we could see whether it's seating correctly or not seating correctly. And this is a tremendously valuable, I think, to low-cost maintenance. You don't need to send a person around on a monthly or a yearly basis to perform this maintenance. It's right there in the power signal if only you had a means to get it. And the Mika platform, obviously, is an exceptional way to do that.
I'll just build on that. We're also seeing, and this is where you can have even double measurements to really triangulate what's going on. There's some great sensing solutions right now that are taking the acoustic and vibration data off the very same motor or pump, and it's overlaying what it's seeing relative to incidents based on that noise and vibration and what's likely happening inside with bearings and cogs and whatnot. And I think as you have that going into algorithms in a local control environment, which is being worked on by two partner companies in the semiconductor space, they're able to step down slow so that there isn't a catastrophic event, that they can actually bring it down to a controlled environment and then drive alert. And then as you're measuring that over thousands of pumps and thousands of scenarios, these algorithms get much sharper because of the group learning. And that's what Watson and IBM is enabling as one example. And then you're able to really get a counter signal that says, if this is happening, then this is likely what's going to happen next. And you've got an alert system with people that are coming down or deployed to go intercept that event. And it's coming really fast. And I think there are many pump and motor manufacturers that are already collaborating with technology companies to go make this happen.
Actually, it's interesting because we do a couple of projects with acoustic analytics, including in the consumer space, where eventually maybe a consumer could record his washing machine, upload that file, and then we'll do some analytics based on that. It's interesting because it seems that it started faster, but after image analytics, right? So we do quality engineering on scratches detection on the back of laptops, aluminum laptops. The speed at which they come out of a line is pretty high, and and those scratches are really small. So we're talking about a very, very low threshold of detection on a high speed rate of images. So that has been done for a little while, but now acoustics, we see it in many different instances. So you combine the two, images, pictures, videos, and acoustic, what's missing? Smell. Would be the next one, I guess.
Okay, so our next question in the domain expertise topic is actually for Nick. Nick, with TI's development of modular sensing solutions for so many application domains, how do you work with specific domain experts to deploy the right products for the right application?
Very good. As I was saying earlier, given the depth and breadth of our portfolio, one of the biggest group of domain experts that we tend to collaborate with are the experts at our customers. So we spend a fair amount of time with them to understand their needs and requirements better, as well as with the rest of our ecosystem partners. Internal to TI, we have established within our product lines for every area that is relevant, such as power management, we have groups of domain experts that are enhancing their learnings and their knowledge up to date on the topic, and they collaborate with our customers just the same. Two more of recent years additions in this space are we have a dedicated team at our circuits and systems R&D organization that's been established to specifically focus on IIoT. And actually, that team collaborates with Harding pretty well. And we have been down that journey for a good while now. And then within our systems engineering teams, where we have groups of system definers and system experts in the industrial space by end equipment and market segment, focused to develop the expertise and the knowledge base that is required so that we can feed all of that into our product definition and development process, as well as to new R&D projects that can go through our Kilby Labs, our circuits and systems R&D organization. Sometimes these lead to definition of projects that will become university collaboration projects for us, or collaboration with other research institutions outside. So from R&D all the way to product development, we are leveraging internal and external collaborators as pockets of experts in these specific spaces, so that we can't have one-size-fits-all solutions. So it needs to be, on one hand, it needs to be flexible. On the other hand, it needs to be very specific to the use case, so that a level of differentiation can be achieved, so that it doesn't cost too much, so that it's not the wrong size, and so on and so on. So we leverage this collective network of experts, internal and external, to help drive that.